Right now, at this very moment, approximately 150 volcanoes are erupting on a single moon in our solar system. These aren't gentle lava flows trickling down mountainsides like Hawaii's Kilauea. Some blast material 300 miles high into space, higher than the International Space Station orbits Earth. Picture fountains of molten rock shooting upward with such violence that the material escapes into the vacuum of space before raining back down as sulfur snow. This moon generates more volcanic power than Earth, despite being only 1/4 our planet's diameter. The surface gets completely rebuilt every million years, erasing any trace of asteroid impacts like a cosmic reset button. This is Io, Jupiter's innermost large moon, where Linda Morabito made the first discovery of active volcanism beyond Earth in 1979. Morabito was examining Voyager 1 navigation images when she spotted a crescent-shaped anomaly rising from Io's limb. What looked like a processing error turned out to be humanity's first glimpse of an alien volcano in action. Io pumps out between 6 times 10 to the 13th to 1.6 times 10 to the 14th watts of heat. That's more than 10 times Earth's total internal heat flow. The Voyager spacecraft revealed a world with no impact craters, meaning the surface is constantly being destroyed and rebuilt. Imagine a planet so geologically active that every trace of cosmic bombardment gets wiped clean faster than new impacts can accumulate. But the real question isn't what's happening on Io, it's why this small moon has become the most violent place in the solar system. The answer lies in a cosmic dance between 3 moons that's been going on for billions of years. Jupiter's gravity stretches Io's solid body by 100 meters twice every 42.5-hour orbit. Imagine the entire moon being squeezed and released like a stress ball in the hands of a giant. This happens because Io is locked in a 1 to 2 to 4 orbital resonance with Europa and Ganymede. Io completes exactly 4 orbits for every one of Ganymede's. The resonance keeps Io's orbit slightly elliptical with an eccentricity of 0.0041, causing its distance from Jupiter to vary by 3,400 kilometers each orbit. Stanton Peele predicted this tidal heating in a Nature paper published just 3 days before Voyager 1 discovered Io's volcanism. The timing wasn't coincidence. Scientists had calculated that gravitational forces should melt Io's interior just as the first images confirmed their predictions. The tidal forces on Io are 20,000 times stronger than what Earth experiences from the Moon. Where our ocean tides rise and fall by mere meters, Io's solid rock bulges outward by the length of a football field twice each day. This creates a global heat flow of roughly 2 to 4 watts per square meter compared to Earth's 0.08 watts per square meter. Every square meter of Io's surface radiates enough energy to power a bright light bulb continuously. Theoretical models suggest Io's orbit may be slowly shrinking while Europa and Ganymede move outward. Though direct observational confirmation over such timescales remains challenging, the 3-moon system exchanges orbital energy like dancers passing momentum between partners. If the 3-moon resonance ever breaks, Io's eccentricity would drop to 0 and its volcanism would shut down. The time frame for this orbital evolution remains unknown, but the current system has likely persisted for billions of years. What we're witnessing isn't just volcanic activity. It's a cosmic squeeze machine that's been operating since the solar system was young. Io's interior likely contains a liquid iron core 650 to 950 kilometers in radius, surrounded by an olivine-rich mantle that may be 20 to 30% molten. Picture a world where the rock itself behaves more like thick honey than solid stone. Galileo's magnetometer detected an induced magnetic signature suggesting a highly conducting layer 50 kilometers below the surface. This magnetic behavior indicates either a global ocean of molten rock or vast interconnected chambers of magma threading through Io's interior like underground rivers of fire. The debate continues over whether the melt exists as a continuous layer or distributed pockets. Some scientists envision a complete shell of liquid rock encircling the moon. Others propose a sponge-like structure where magma fills the spaces between partially solid rock. The surface temperatures at active vents reach 1600 Kelvin. That's hot enough to melt copper and comparable to Earth's most ancient volcanic rocks. These aren't just hotspots, but furnaces that would vaporize most metals instantly. Io's lithosphere must be at least 12 kilometers thick to support mountains like Beausoleil Montes, which rises 17.5 kilometers high. That's twice the height of Mount Everest, built not from tectonic collision but from volcanic construction. The 1997 eruption at Pilon Patera reached temperatures exceeding 1800 Kelvin, hotter than typical terrestrial basalt. These extreme temperatures suggest Io taps into primordial heat sources that have long since cooled on other worlds. Recent studies of hotspot P63 using Juno's infrared data suggest previous power estimates may be off by an order of magnitude. The major volcanoes are displaced 30 to 60 degrees east of where tidal heating models predict maximum energy dissipation. This offset suggests either magma migrates hundreds of kilometers before erupting, or a fluid magma ocean alters the heating pattern. Either way, Io's interior is fundamentally different from any world we know. The moon operates by rules that challenge our understanding of planetary physics. Loki Patera spans 202 kilometers and produces roughly 10% of Io's total heat output. This massive lava lake undergoes episodic brightenings every few hundred days as waves of crustal foundering expose fresh molten lava. Imagine a lake of liquid rock larger than Connecticut, where the surface periodically breaks apart and sinks, revealing the glowing interior beneath. During these events, Loki's power output increases by up to 10 times, reaching tens of gigawatts. That's enough electricity to power several major cities. Peli, the volcano where Linda Morabito first spotted volcanic activity, maintains a lava lake surrounded by a 1,200-kilometer diameter ring of red sulfur fallout. The sulfur compounds paint Io's surface in shades of yellow, orange, and red like an artist's palette of fire colors. Juno's recent polar observations discovered active volcanic clusters at both poles, challenging models that predicted heating only at low latitudes. The discovery means Io's volcanic violence extends from equator to pole without interruption. Some lava flows like Amarani stretch over 300 kilometers. That's longer than the distance from New York to Washington, D.C. These flows move at walking speed, but carry enough molten rock to bury entire cities. The Pilon eruption emplaced a 70-kilometer flow in just 2 weeks with evidence of 10-meter-thick lava rafts. Imagine house-sized chunks of cooling lava floating downstream like icebergs in a river of fire. Lake Fluctus covers 125,000 square kilometers, an area larger than Nicaragua. The volcanic activity completely resurfaces Io every 1 to 3 million years, explaining why no impact craters survive. Recent eruptions at hotspots P139 and PV18 each exceeded 1 terawatt of power output. Single volcanic events generate more power than entire nations consume, transforming the scene faster than erosion can wear it down. These aren't just big numbers. They represent geological processes operating at scales that dwarf anything on Earth. When a single volcanic event can generate more power than many nations consume, we're witnessing planetary-scale engineering driven by gravitational forces alone. Io has become a laboratory for extreme volcanism, showing us what happens when tidal forces turn a world's interior into a perpetual furnace. Io's 400 active volcanoes represent the most extreme geological activity in the known solar system. This violence stems from a precise cosmic clockwork, 3 moons locked in gravitational resonance for billions of years. The same forces that make Io a hellscape also maintain Europa's subsurface ocean and may have shaped the evolution of the entire Jupiter system. The resonance that powers Io's volcanoes simultaneously keeps Europa's ocean liquid beneath kilometers of ice, creating 2 completely different worlds from the same gravitational dance. Future dedicated missions could measure Io's tidal deformation directly and solve the magma ocean mystery. Scientists have proposed orbiters that could track Io's shape changes in real time, finally answering whether a global ocean of molten rock lies beneath the crust. The Io Volcano Observer mission concept would use radar to peer through the volcanic haze and map the interior structure with unprecedented precision. Other proposals include heat-resistant landers that could survive long enough to sample volcanic gases directly, revealing the chemical composition of Io's interior. But for now, Io remains our solar system's most active world, a place where the interior of a planet has been turned completely inside out. Every 42.5 hours, Jupiter's gravity kneads this moon like cosmic dough, keeping 400 volcanoes erupting in a display of violence that makes Earth's most powerful eruptions look gentle by comparison. The next time you see Jupiter in the night sky, remember that orbiting nearby is a world where the ground itself burns, where mountains of fire rise and fall, and where the very rocks flow like water in an endless cycle of destruction and creation.